The next speaker is Anna Seigel here from Harvard University. Her talk is Invariant Theory for Maximum Likelihood Estimation.
Hi everyone. Let me just see if I can remove the next part of the slide n+1 from the view of slide n. Okay, yeah, that looks better. All right, hi, thanks a lot, Bernd and Lauren, for the invitation, and thanks, Brad, for the introduction. It's great to be here. Thank you all for coming. Today, I'm going to be telling you about some work we've been doing on invariant theory for maximum likelihood estimation. So this is based on some joint work with Carlos Améndola, Kathlén Kohn, and Philipp Reichenbach. Please stop me at any point if you have any questions. I'm really happy to take questions at any time throughout the talk. So as a very high-level overview of my talk, today I'm going to be talking about some connections between statistics, specifically maximum likelihood estimation, so estimating parameters in statistical models using data, and invariant theory, so looking at groups acting on spaces and what happens to points under the action of that group. So I'm going to be connecting these two sides, and in the setting I'm talking about today, this connection takes place via polytopes. So the goal of the talk is this arrow. Oh, that's not the correct way to point. This arrow here, but I'm going to be obtaining this arrow from this one and this one.
Let me try.
Maybe there's also like a laser pointer.
Yeah, this is a great 19th century technology.
Oh, thank you. Okay, so we're going to be making this connection via polytopes. So on the way, we'll see some polytopes like these ones. So if you like, you can think of these as base polytopes of matroids, if you like, or just as polytopes. Okay, and maybe we'll also see some connections to the talks from earlier today as we go. Okay, so I'd like to start by talking about this connection between statistics and polytopes in a first example. So here is polytopes and statistics in our first example. So the model I want to look at is the independence model on two binary random variables. So this model takes 4 possible states. So the random variable x1 can take values 0 or 1, and x2 can also take values 0 or 1. And the independence model says that this joint probability, so the probability x1 takes a value I and x2 takes a value j, is just given by this product. So I obtain this joint probability by multiplying the probability x1 takes a value I times the probability x2 takes the value j. All right, so what the independence model means is that this probability mass function, which I can write as a 2x2 matrix of non-negative numbers, is rank 1. So its entries look like this. I can write the 2x2 matrix as the outer product of 2 vectors, one with entries lambda 0 and lambda 1, and the other with entries mu 0 and mu 1. All right, and we can also describe this model, this rank 1 probability mass function, implicitly. So the model is defined by the vanishing of the determinant polynomial. And if we look inside the 3-dimensional probability simplex, this is what the independence model looks like. So, all right, yesterday we saw the example where our 2 random variables are you wearing a mask, yes or no, and are you wearing glasses, yes or no. So we might wonder whether those 2 things are independent or not. So that's an example to keep in mind. All right. we want to estimate parameters in our model in the presence of some data. So now the setup looks like this. So here's our cartoon picture of the probability simplex in which our statistical model lives. And then we also have some data points, so maybe our empirical observations of how many people are wearing glasses and a mask, or the other three possible options. Okay, so we can collect some data. So we'll say Uij is the fraction of times that we observe this joint state, I and j. So our data is then also a 2x2 matrix of non-negative numbers that add up to 1. So I made sure they add up to 1 by just taking the fraction of times we observed each state rather than the total count. Okay, and then the function that we are looking to maximize is also a function that we've seen earlier on today. So we want to look at the product over all possible pairs I and j of pij to the uij, where uij is known. These are our observed counts. And these pijs are unknown, but they have the form required by our model. So this likelihood function can then be rewritten as a function in our 4 unknown parameters, lambda 0, lambda 1, mu 0, and mu 1. Okay, so this is how we can go about doing maximum likelihood estimation for this independence model. And we could compute the partial derivatives of this and set them equal to 0 to identify the possible values for our parameters that maximize the likelihood function. And this is what they look like. So lambda, our best estimate for lambda 0, we write as lambda 0 hat, and it should be equal to u0 plus. So the plus means that we're summing over the possible values for the second index. And so on for the other 4 unknown parameters in the model. Okay, so I haven't said much about polytopes so far. I mean, the model lives in a polytope, so it lives in the probability simplex, but this is not the polytope that I'm talking about. What I'm talking about is another polytope that we see that captures whether our maximum likelihood estimate exists or not. So we can see that our maximum likelihood estimate, well, we have this formula here, which for any vector u writes down what the maximum likelihood estimate will be. But we're interested in a model that lies strictly on the interior of the probability simplex. So we want every parameter to be strictly positive. We don't allow zeros. So now we get some condition on whether these 4 linear functions are strictly positive or not. And the condition has to do with a certain polytope. So our maximum likelihood estimate in the model exists if our data vector u lies in the relative interior of this polytope. So this is a polytope in R4. I'm writing it as the convex hull of 4 vectors in R4. And I'm also writing a vector in R4 in this 2x2 form to keep the multi-index structure of the original model. So given some vector u, we want to know, does it lie in the relative interior of this polytope? And if it does, then our MLE exists, and if it doesn't, then the MLE does not exist. Yeah, maybe I'll pause here for any questions. Okay, so this is how a polytope arises in deciding for a statistical model, does my maximum likelihood estimate exist? Yes or no? So can I find the choice of parameters that optimize the likelihood?
I have a question now. So you define the Uij to be a fraction. The sum of the u's should be 1. But in your matrices, the sum is 2. Scale by a half?
Yeah, maybe. Yeah. Yeah, possibly. So, okay, so we can always work with our Uij data being the actual counts, so the number of times we observe each state, and then we have to make sure we divide by the total number of counts appropriately.
Then you should take Kohn, and you go this would be Kohn.
Yeah. So it's possible that we need to. Yeah, exactly. Yeah. Okay. Yeah, we'll see. All right, so what does this look like then for a more general model? What's the appropriate generalization of this connection between the statistical setting and our polytope? So I'm going to be talking about log linear models. So these are a collection of distributions whose logarithm lies in a fixed linear space. So my linear space, we've seen today a couple of times that this idea of taking a matrix and then taking the row span of the matrix. Here I'm interested in those points in the probability simplex whose logarithm lies in the row span of this matrix. So this is a log linear model rather than a linear model. And I'll call it MA. So it's determined by matrix A up to row span. So two matrices with the same row span will define the same log linear model. So A is a matrix of integers. And we'll assume that the all ones vector lies in the row span of our matrix A. Yeah, that's what was confusing me a bit about rescaling the matrix A. But yeah, it's okay. We can rescale A. All right. So an example for what our matrix A could look like is this matrix here of zeros and ones. So if this 4x4 matrix of zeros and ones is our matrix A, what is its corresponding log linear model? So what does the set of distributions look like whose logarithm lies in the row span of this matrix? Well, I've indexed the rows and columns of this matrix in a sort of suggestive way. So a P vector that's in the row span of this matrix has the property that, vector P that lies in the log linear model, so its logarithm lies in the row span of this matrix. This means that log of Pij is lambda I plus mu j. So for example, in the 0, 0 entry, we get lambda 0 plus mu 0. All right, so then if we take exponentials on both sides, we see that we've recovered this product form where the joint probability Pij is equal to the product of something just involving I and something just involving j. So this is our 2x2 independence model. So if we want, we can think of the 2x2 independence model as the log linear model corresponding to this matrix A. Okay, and then there's lots of other examples of statistical models that are log linear models for some choice of matrix A. So we can put discrete graphical models or hierarchical models in this context. For certain, so in fact, in all of these examples, we'll end up with a matrix A whose entries are zeros and ones. Okay, and then as before, we have this setting where we have our model living inside the probability simplex. We then have some observed data, and we want to find its best approximation on the model. So the choice of parameters that best fits the observed data. Yeah. Was there a question? Okay, and a theorem of Birch, or attributed to Birch, says that the MLE, given some data U, is a point in the model, if it exists, such that applying this matrix A to our point P hat gives us the matrix A applied to our data U. So in the previous example, we saw this in the context of the independence model. So we can take our vector of observed counts, we multiply it by the matrix A, and we end up seeing like P00 plus P01. So that's what gave us this P0 plus that we saw in the independence model example. Okay, so then one question is about the existence of the MLE. So this gives a description for it, or an equation that has to hold if it should exist. And this can be thought of as matching sufficient statistics to the data. So that's a statistical description of this equality here. Then a result due to Ericsson, Feinberg, Rinaldi, and Sullivan from 2006 then enables us to characterize the existence of the MLE in our log linear model. So we have that the MLE given U, given our data U, exists in the model, if and only if. So we then have our matrix A applied to our data vector U, and we want this to lie in the relative interior of the convex hull of the columns of the matrix A. So in this example, we can take these 4 columns here. So these are the 4 vectors in R4 that we saw before for the independence model. And we're interested in whether our data under the matrix A lands in the relative interior of this polytope or not.
Sorry, did you say why you take integers for the entries to the matrix, or rather than
Say again? Why do I take integers?
Integers for entries to the matrix?
That's a good question. So in all of these examples, it turns out to be the case that we end up with the model being captured by a matrix A whose entries are all zeros and ones. So that's saying that down each column, we just have whether each parameter participates in that entry of our probability mass function, and that's just a yes or no. But we could extend this to other integer values. It's possible. So are you asking why the entries are integers here, or why they're zeros and ones?
Well,
I guess
yeah.
Yeah. So I think it's an interesting question from the perspective of the statistical interpretability. So in this case, well, the independence model has this nice interpretation where we've sort of factored our probability distribution into factors involving certain variables and other variables, and graphical models and hierarchical models extend that to higher dimensional settings, where we then have certain groups of variables that participate in certain entries of our probability mass function and so on. It could be the case that certain variables participate with higher powers, and I suppose it's an interesting question of how best to think about that statistically. On the mathematical side, we can populate the matrix with whichever integer entries we want, but it's probably easiest to think of examples involving glasses and mask wearing when we have zeros and ones. Thanks for the question. Any other question? All right. So I said I would also be talking a bit about invariant theory. So let's see the group action I'm thinking about. So I'll denote by GTD the complex diagonal invertible D by D matrices. Okay, so that's just a tuple of D non-zero complex numbers, which I think of as the diagonal entries to some diagonal matrix. And now we have an action of this group on a complex vector space, CM. That's determined by a matrix of integer entries A together with a vector of integer entries B. So I'll call this B vector the linearization following the invariant theory nomenclature. So how does a tuple of D non-zero complex numbers act on a vector of M complex numbers? Well, we multiply by this diagonal matrix where theta to the aj minus b, okay, theta is a vector of length d, aj is a column of the matrix A, so aj is also a vector of length d, and b is also a vector of length d. So by vector of length d to the vector of length d, I mean take theta1 and raise it to the power of the first entry of aj minus the first entry of b, and so on. All right, so this is how our d by d diagonal matrix transforms our m-dimensional vector space. And what does this have to do with the statistical setting I was talking about before? Well, let's try an example. So if we take our matrix A from before, so this was our 4 by 4 matrix of zeros and ones, and we can let our linearization be 0, then how does GT4 then act on C4 according to this matrix and this linearization? Well, we're multiplying by this 4 by 4 diagonal matrix. So the first entry gets multiplied by theta1, theta3. So we look down the column of A and see which exponents participate. The second entry gets multiplied by theta2, theta3. The third entry gets multiplied by theta1, theta4. And the fourth entry gets multiplied by theta2, theta4. And we don't subtract anything from any of these exponents because the linearization is 0. Okay, so we're multiplying by these 4 by 4 diagonal matrices. That's our action. Which statistical model is parameterized by this torus action? Well, this is a bit of a bad question because these are complex numbers. Everything is complex, so perhaps the answer is, well, no statistical model is parameterized by this torus action. But on the other hand, we can start with the all ones vector and think about what happens to it under matrices of this form. Well, we end up with 2 by 2 matrices that look like this if we reshape our vector of length 4 back into a 2 by 2 matrix. And here we have, okay, a rank 1 matrix. So we have theta1, theta2, theta3, and theta4. So this is our 2 by 2 independence model reappearing again as a particular part of a torus orbit. Okay, so where do polytopes show up in the context of invariant theory? Well, here's the setting that we'll look at today. So we have a group G which acts linearly on a space V. So the orbit of a point under the group is the set of all points G dot V as G ranges over the group. And the stabilizer is the set of group elements that fix a particular point. And this is the picture to have in mind. So we have point V in our space. We consider its orbit. So this is its orbit, G dot V. And the capacity is the infimum, as we range over the group, of the distance of G dot V to the origin. So as we range over this orbit, G dot V, we're looking to minimize its distance to the origin, which for this picture here, it will be minimized at this distance here. All right, and there are various definitions that capture what an orbit looks like under this idea of looking at distances to the origin. So we say that a point is unstable if the capacity is 0. So if this closest distance to the origin is 0. Conversely, a point is semi-stable if the capacity is strictly positive. And then there are two strengthenings of semi-stability. So a point is polystable if it's non-zero and the orbit is closed. So we can think about why, if you're polystable, you would have to be semi-stable. And finally, a point is stable if it is polystable and the stabilizer is finite. Okay, so we don't need to worry too much about these definitions unless you would like to. If you would like to, then as some examples, we can think about which of these definitions apply in the case where we have a finite group, which apply when we have the group of m by m invertible matrices acting on a vector of length m. And then as a first example where we'll see all of the definitions appearing, you can look at a product of two special linear elements of the special linear group, so a pair of matrices of determinant 1 acting on the space of rectangular M1 by M2 matrices. Okay, so what does all this have to do with polytopes? But first, so the unstable points, so this is an object of classical interest. It's the null cone as studied by Hilbert. So this is the variety given by the vanishing of all homogeneous invariants in positive degree. So this is a way to rephrase the condition for being in the null cone in terms of this capacity distance. Okay, so what does this look like for our particular action? Well, we have a torus action, which I said was given by a matrix of integer entries. We can define for a vector x a certain polytope, which I'll call P sub x of A. So this is the convex hull of certain columns of the matrix A. And how do we know which columns to take? Well, we look at the indices that lie in the support of our vector x. So x is a vector of length m, and if it has full support, then this polytope P sub x of A is just the convex hull of all the columns of the matrix A, and then if it has smaller support, I just take the submatrix, the convex hull of the columns of a submatrix of the full matrix A. Okay, and then the Hilbert-Mumford criterion for this action tells us that we can reinterpret each of these definitions of stability as a certain condition on these polytopes. So we have our torus action of this group of diagonal matrices, and it's given by a matrix A, a linearization B, and we're looking to determine for some vector V whether it's unstable, semi-stable, polystable, or stable, and here are the 4 conditions. So it's unstable if and only if our B vector is not in this polytope, PV of A. Conversely, it's semi-stable if and only if B is in PV of A, and then it's polystable if B is in the relative interior, and stable if B is in the strict interior of this polytope. All right, so now we have all the ingredients to connect these polytopes to our invariant theory setting, and we can study what the null cone looks like. So I said before, the null cone is where this ring of invariants all vanish. So this ring of invariants are the polynomials, functions of V that are unchanged under our group. Okay, and I also said before that a point is unstable if B is not in the polytope PV of A. So this means we can see in this case what the irreducible components of the null cone look like. So the irreducible components will be certain linear spaces, so spanned by some basis vectors Ej, as J ranges over a certain indexing set, and the indexing set is given by Pj of A being a maximal subpolytope of our polytope that doesn't contain our given vector B. So here's an example of the same polytope given by vertices A1, A2, A3, and A4, and then 4 different choices of B vector. And for each different choice, we can see what the irreducible components of the null cone are going to look like. So we're looking to find a maximal subpolytope not containing our B vector. So in this example here, our maximal polytopes that don't contain B are, we can take A1, A2, and A3. So that will give us one component, A1, A2, and, oh no, sorry, that's A4. A1, A2, and A3 is this one, A1, A2, and A4, and then A3 and A4. So those are our 3 irreducible components. Similarly, the red triangles or edges denote the each of the irreducible components. Okay, and we can also read off from this polytope description what the generators of the null cone will look like. So a vector x is in the null cone, provided all of these products vanish, where now J is a different indexing set, and it's defined so that Pj of A is a minimal subpolytope that contains our vector B. So the products then that need to vanish in this case, we can check A1, A3, and A4 and make sure that that's 0, and we can check A2, A3, and A4 and make sure that one is 0 as well. Okay, so this is to illustrate this nice connection between polytopes and the null cone, i.e. a point being unstable, and we can have similar descriptions for these other notions of stability. Okay, so this then brings us to being able to connect the invariant theory setting with the statistical setting. So this is something that we've been working on recently. So today I'm mostly talking about this first paper here, which is in algebraic statistics, and we have a couple of other related works. So these are the 2 settings that we are interested in connecting. So there's this invariant theory setting where we have a point and its orbit, and we're looking at distances to the origin. And this is the statistical setting where we have our statistical model and some data, and we're looking to find the parameters that best fit the data. And we saw in the invariant theory setting these 4 notions of stability. And on the statistical side, there are also 4 possibilities that arise for what can happen as we attempt to maximize the likelihood function. Or in fact, these are also 4 possibilities for what can happen as we attempt to maximize any function. So it could be unbounded from above. It could be bounded from above. So these 2 are opposites. If it's bounded, it could attain its bound. In our case, a point where the function attains its bound is a maximum likelihood estimate. So this is the case where we have existence of the maximum likelihood estimate. And then a strengthening of this is that our function attains its bound at a unique point, which in this case means that the maximum likelihood estimate exists uniquely. Okay, so we've already seen how something about how these different notions relate to polytopes, and also something about how these different notions relate to polytopes. So what I'll do in the remainder of the talk is sort of mesh this all together so that we can relate these 2 sides via the polytopes. Yeah, are there any questions before I continue? All right, so then zooming in on our setting of interest, we have our invariant theory context has a torus action defined by a matrix of integers A, and our statistical setting, this is a log linear model, which is also defined by a matrix of integers A. Okay, and here's what the correspondence looks like. So unstable points do not arise. A point is semi-stable if and only if what's known as an extended MLE exists and is unique. So an extended MLE allows us to have zeros present, which is something we wanted to exclude in general. A point is polystable if and only if the MLE exists and is unique. And the stable case also does not happen. Okay, so there's a lot that I'm not saying here, but which I will say now. So these are like the terms and conditions of this correspondence. So we are looking at a matrix of integers, and we require that the all ones vector is in its row span. Okay, we have some data, which now we're actually using count data rather than fractions. So we want our entries to sum up to some value n. And now I need to tell you what the group action is. So in fact, we're not looking at the torus action defined by the matrix A, but a related action given by the matrix n times A, so rescaling all of the entries by n, and the linearization we're looking at is also a vector of integers that we get by multiplying A times U. Okay, and then the proof idea is to relate these polyhedral conditions for maximum likelihood estimate existence to the Hilbert-Mumford criterion, where we got these polytopes from the stability conditions. Okay, so I also want to say something about how to actually find the MLE using the group action. So the Kempferness theorem says that the point that minimizes the distance to the origin is given by the vanishing of the moment map, and we can apply that general result in our specific setting to get a formula for what is happening at this point here, where the distance to the origin is minimized. So the infimum distance to 0 on the orbit closure is attained at a point x that satisfies this equation here. So x to the 2, this is the vector whose jth entry is given by the mod of xj squared. Okay, so this is a condition involving the entries of the matrix X. And it's closely related to the conditions that are required to hold at a maximum likelihood estimate. So in fact, we can obtain the MLE given U in our log linear model from our vector x just by dividing both sides of this equation by this mod x squared. So our MLE looks like this, x to the 2 divided by mod x squared. So how can we prove this? Well, Birch's theorem, which I mentioned before, says that the MLE given some data u is a point that satisfies this equation, Birch's equation. So dividing through by this mod of x squared, we see that this is exactly the same as this equation here. So all we need to check is that this vector actually lies in our model. And we can do that by using the implicit description of the model as a toric variety. So as these differences q to the v minus q to the w, where v and w are vectors of integers that satisfy av equals aw. Okay, in the interest of time, I won't say much about algorithms to compute the MLE or algorithms to minimize the norm, but I'm happy to talk more about this if anyone wants. And yeah, that's it. Thanks.